Okay, now we're starting to look at dealing with bonds and delta H values or enthalpy values. So first thing at the top here, remember the delta H reaction of a reaction is a way of describing the potential energy, because remember, potential energy can be stored in bonds, which reflects the changes in bonds and in intermolecular forces. So whether we're breaking or forming bonds, or whether we are separating molecules or putting molecules together, that's what it's talking about. So we're going to calculate these by looking at the things below here. So a bond enthalpy is a value that represents the bond strength, or AKA how much energy does it take to break that bond. Specifically, it's the amount of energy that needs to be added to cleave the bond or to break the bond. That's what that means. Chemical bonds form because they're thermodynamically favorable, and breaking them requires adding energy. So this is where I want you to write in your paper. Just remember, breaking bonds is it endo or exo? Well, we just said it takes energy to do so. So that's endo. And forming bonds, when you do so, you give off heat energy, so it's exo. Okay, so just make sure you always have that straight in your mind when you're looking at stuff like this. Okay. All right. As such, chemical bonds form because they're thermodynamically favorable, and breaking them requires adding energy. As such, bond enthalpy values always have a sign, a positive sign, because we're adding energy, so that's indicating endothermic, in our units kilojoules per mole. When bonds break, energy is released, and they will have a so. This is supposed to say something else. When bonds break, energy is not released, because we just said when bonds break, it's endothermic. It should be energy is absorbed, and then they will have a positive sign. Okay, so just make sure you put that, change that in there. Bond enthalpies can be used to estimate the enthalpy of reactions, identify which bonds will break, and find their bond enthalpies. And it says on a chart on a page, but I'm just going to say online because we can easily just look up bond enthalpies online for both of these. There's no need to say a page in our book. It's probably just going to be easier to search it. Or if it's a question on an exam or a test, we'll give you those values. It's not like you have to memorize it. Now, I have a quick question. So, what type of bond would you expect to have the highest bond enthalpy? So, if you think about it, what type of bonds do we know about? We know about single, double, and triple bonds. So, single bonds are the easiest to break. Double bonds are a little harder, and then triple bonds are even a little harder than that. So, triple bonds would have a high um, enthalpy value, whereas a single bond would be a lot lower. Okay, so that's one thing I just wanted to point out to you guys. Okay, as we continue on, there's a formula here, and it says do the calculation, the sum of what's broken minus the sum of what's formed. So if we look at a reaction, the substances that are broken are going to be the reactants, and the substances that are reformed are going to be the products. So just to put that in there. So that's how you do that. And we'll do some practice problems down here at the bottom. If we want to calculate energy changes for when we have IMF, so that's where we have these phase change diagrams, or these heating curve is what we have here. Let me move this so you guys can see it. Okay. If you want to calculate how much energy it takes to raise the temperature of a substance from some value to another, you need to calculate how much energy is absorbed by the substance at different stages throughout the heating process. So here we have 1, 2, 3, 4, 5 different stages we got to go through. To do this, you'll need to know the specific heats for the substances at different phases, as well as the heats of fusion and vaporization. Again, on a test, those will all be given, but to be able to do these, you need them here. Sometimes these vary a little bit. We're going to use 2.06 joules per gram degree C for the specific heat of ice, and we'll use water. We'll use 4.184, and sometimes you'll see me use 4.184, sometimes 4.18, whatever. It's not that big a deal. The molar heat of fusion is just going to be 6.01, and that's kilojoules per mole. Put that value in there. And that's the energy needed to melt or freeze 1 mole. Melt or freeze 1 mole. And it would be of a certain substance. In this case, is water. I'll put here water. The heat of vaporization. Right, sorry about the bell. Okay, heat of vaporization value is 40.7 kilojoules per mole. And that we use when we're condensing or vaping. Okay, and that's for water as well. Okay, so to calculate the energy added when a substance is in a specific phase, we use a formula. So that means it's not changing phases. This is when we have a temperature change. Okay, we're going to use Q MCAP. To calculate the energy added when the substance is undergoing a phase change, you're going to have Q equals N, which is number of moles, times either H vape, or, depending on what's happening, or Q equals N times H fusion. And again, it just depends on what process. Is it in this case melting or freezing, or is it in this case evaporating or condensing? So you have to decide. Then when you're done, you just add up the total value to get the total energy, Q total. You can do capital Q or lowercase q, whatever. Okay, so let's go through our practice problems here. Okay, so I rewrote the reaction they gave us on number 11. We're starting to look at those questions. It says use the bond energy values. And I looked up all the bond energy values and put them here so we can just use those. And we're going to calculate delta H. So if you remember back up to the top, like at number 3 at the top of the page, to do the calculation, it's the sum of the reactants minus the sum of the products for the. So I'm just going to write down what we have here. So under each thing. So for an H to C bond, if we look at our chart, an H to C is 414 kilojoules per mole. So I'm going to put that there, 414. And then the C triple bond to an N, because it matters, it's different. That one's 891. And then for an H to an H bond, it is 436. But notice we have 2 of them, so I'm going to put 2 in front of there. Because if we were to draw this out, it would be H to H. Oh, you guys can't see that, sorry. I'm sorry, let me move this little guy. Okay. All right, so I just put 2 times 436, and then it would be like, it's 2 of these. So that's why I put 2 times 436. And then over here, we have 1, 2, 3 C to H bonds. So what is the C to H? 3 times 414. And then we have the C to the N plus the C to the N, which is 305. Plus how many N to H's? 2 N to H's, so 2. N to H is 389. And let me write this side in the same form I did over here. Okay, so we have, I'll just write it out, the whole thing. 414 plus 891 plus 2 times 436 minus, so that's all add together, sum together, minus 3 times 414 plus 305 plus 2 times 389. Okay, so then we would calculate a delta H. So let's see what you guys get. When I did this, I like to write out what I got for each side. So I wrote for this one, I got 2177 for that side and 2325 for this side. So we know we're going to get a negative value. So I got negative 148. And the other type question they could ask you is this endothermic or exothermic? And you know, because it's negative, this is exothermic. Okay. All right, so the next problem, there's another reaction just like this. And I want you to pause this and try it real quick because it's the same situation. See if you can get it. And I have all the values here. So if you need to look at what the delta H values, again, you can just search for enthalpy values for, the different bonds. It's hard to get them all in here because I wrote it so big, but there they are. Okay, I'm going to pause it because I want you guys to pause it and try the next one. Okay, let's do this. Let's do this next one really quick. It's, by the way, if the formulas aren't drawn out like this, like if this just said N2H4, it would be to your advantage to draw it out because in this case, and it doesn't have a double bond, but let's see, this would be 10. Okay, this should be 12, 14 like that. 2, 4, 6, 8, 10, 12, 14. Just kidding. It can't be like that because that would be too many on the ends. It's going to be like that. 2, 4, 6, 8, 10, 12. Is it N2H4? Okay, well, all right, don't do this because they must want us to use this one. Sorry for the issue. Let's just use what they have as a picture and not overanalyze it. Okay, so we have 4 N to H's. So 4 times, what's the N to H value? Right here, 389. Sorry, you can't see it. 389. And then plus the N to N value here, which they go N to N is 163. Plus 2 times F2, which is 159. All minus the N triple bond, 946, plus 4 times HF, which HF is 562. Okay, and then you just calculate that and get your answer. I'm going to pause it so I can calculate it. Okay, now you can see what I ended up getting. I highly recommend doing the sides, like figuring out what this side is, which I got is 2037, and doing this side, which is 3194, and then subtracting, because it's easy to make a mistake if you plug the whole thing in. And you can see again, it's definitely exothermic. Okay, I'm going to try to speed run this last part because we only have a few minutes left on the video, but we're looking at, let's look at number 12 here. So we have from -3 degrees Celsius to 75 degrees Celsius. And this is water. So you have to break it into parts. So water is ice from -3 to 0. From 0 to, or sorry, at 0, it's doing something. And then from 0, it's melting here. So I'll put it here, melts. And then from 0 to 75, the water warms. So remember, we're alternating equations here. If there's a temperature change, which there is in this one and this one, we're using QMCAT. We just have to make sure we use the correct specific heat. So we're going to do Q equals, our mass they give us is 18.02 grams. Okay, and our specific heat for ice we're going to use is 2.06. And that's joules per gram degree C. Our change in temperature is 3 degrees C. So if you multiply that when you get your joules, it should be 111.37 joules. This one, we're going to use the Q equals N, which is moles, times H fusion, which is a constant. So Q equals, incidentally, this is 1 mole of water, so it's going to be 1 mole times H fusion, which we know is 6.02 kilojoules per mole, because I gave it earlier. And let's convert this to joules so we can calculate this all together. So you're going to get 6.02 kilojoules, so 6,002 joules. And let's go to the last step. So last step, Q equals mass is 18.02. Our specific heat now, it's water, so it's 4.18. I'm just use 4.18 joules per grams degrees C. And then our change in temperature here is 75 degrees C. So when I multiply all that out, my Q, I got 5649.27, and that's joules. So then I just need to add them all together to get a Q total. And Q total ends up equaling 11,770.64, and that would be joules. Okay, hope all this made sense. Thanks.